For decades, the global semiconductor race has been measured by a familiar set of milestones. Who can manufacture the smallest transistors? Which company can produce the fastest processors? Which nation controls the most advanced chip fabrication plants? Those questions have dominated industry headlines, investment decisions, and government policy alike. But while the spotlight remained fixed on silicon itself, another technology was advancing quietly in the background, one that sits beneath every advanced processor yet rarely receives public attention. That overlooked component is the substrate, the foundation that supports a chip, connects its internal components, and helps it operate under extreme conditions. For years, it was viewed as a mature technology that simply kept improving alongside the rest of the industry. Today, that assumption is beginning to change. As artificial intelligence pushes computing systems beyond previous engineering limits, the substrate has evolved from a supporting role into a critical factor in overall performance. And increasingly, engineers believe the next major breakthrough may not come from making transistors smaller, but from replacing the material underneath them. The surprising candidate is glass, not ordinary glass, but an ultra-precise material, engineered specifically for advanced semiconductor packaging. It represents a subtle but potentially transformative shift, one that could influence the future of AI computing, reshape global supply chains, and redefine where the next phase of semiconductor leadership is won. Artificial intelligence has changed more than just the software running on computers. It has fundamentally changed how the hardware itself is designed. The processors powering today's largest AI models no longer rely on a single monolithic chip. Instead, manufacturers increasingly assemble multiple specialized chiplets into one tightly integrated package, allowing each component to perform a specific task while working together as a unified system. This design offers enormous performance advantages, but it also introduces a new engineering challenge. As more chiplets are packed into a single package, the network of electrical connections grows dramatically. Billions of signals must travel between processors, memory, and communication components every second, all while operating under heavy computational loads and generating significant amounts of heat. At the center of this complex system sits the substrate. Although rarely discussed outside semiconductor engineering, it performs several essential functions simultaneously. It provides the mechanical support that holds the package together, routes electrical signals between components, and helps maintain stability as temperatures fluctuate during operation. For decades, manufacturers relied on advanced organic materials made from specialized resins and polymers. These substrates performed exceptionally well when processors were smaller and computational demands were relatively modest. As the semiconductor industry evolved, incremental improvements were enough to keep pace with each new generation of chips. Today's AI hardware presents an entirely different challenge. Processor packages continue to grow larger, connection densities keep increasing, and power consumption reaches levels that were once unimaginable. Under these conditions, even microscopic material expansion caused by repeated heating and cooling can gradually reduce alignment accuracy, affect signal quality, and complicate long-term reliability. What was once considered a supporting component has now become one of the defining factors in overall chip performance. As AI systems continue to scale, the industry is discovering that future breakthroughs may depend just as much on the foundation beneath the processor as on the processor itself. As semiconductor companies continue pushing AI hardware to new levels of performance, they are running into a limitation that has little to do with transistor design. The challenge lies in connecting increasingly complex processors together without sacrificing speed, efficiency, or reliability. Modern AI accelerators process enormous volumes of information simultaneously. Instead of relying on a single computing die, they combine multiple chiplets, stacks of high bandwidth memory, and dedicated communication modules into one densely integrated package. Every one of those components must exchange data continuously, often at speeds measured in hundreds of gigabytes per second. That level of communication places extraordinary demands on the substrate beneath the package. Unlike earlier generations of processors, today's AI chips generate intense heat over prolonged periods. Every training session or large-scale inference workload causes temperatures to rise and fall repeatedly. Although these temperature changes may seem insignificant, they create tiny cycles of expansion and contraction within the materials supporting the processor. For traditional organic substrates, those microscopic movements are becoming increasingly difficult to manage. Individually, each shift is almost impossible to measure. But when billions of electrical pathways are separated by incredibly small distances, even the slightest movement can affect how accurately signals travel across the package. Connections that were perfectly aligned during manufacturing may gradually drift, introducing electrical noise, increasing resistance, or reducing transmission efficiency. These issues rarely produce dramatic failures overnight. Instead, they appear as subtle performance losses, inconsistent behavior, or reliability concerns that become more significant as chip complexity increases. Engineers often spend months optimizing designs simply to compensate for the physical limitations of the substrate itself. The challenge becomes even greater because AI processors continue growing in both size and capability. Every new generation demands more memory channels, more communication links, and tighter spacing between electrical connections. At some point, simply refining existing materials no longer delivers meaningful improvements. This marks an important turning point for the semiconductor industry. Rather than treating the substrate as a passive platform supporting the processor, engineers now view it as an active contributor to system performance. The quality of the foundation directly influences how efficiently data moves, how well heat is managed, and how reliably the entire package operates throughout its lifespan. That realization is driving one of the industry's most significant material transitions in decades. Instead of asking how much further traditional substrates can be improved, companies are beginning to ask a different question altogether: whether an entirely different material can eliminate these limitations from the start. Finding the problem is only half the battle. The harder question is how to solve it. After years of research into advanced packaging materials, many semiconductor companies have reached a similar conclusion. Improving traditional substrates may no longer be enough. Instead, the industry is beginning to explore an entirely different foundation. That foundation is engineered glass. At first glance, the idea sounds almost contradictory. Glass is commonly associated with fragile household objects, not with the world's most powerful AI processors operating around the clock inside massive data centers. But semiconductor-grade glass bears little resemblance to ordinary consumer glass. It is manufactured with extraordinary precision, designed specifically to meet the demanding requirements of advanced chip packaging. Its greatest advantage is dimensional stability. Unlike organic materials, which naturally expand and contract as temperatures change, engineered glass remains remarkably stable throughout repeated heating and cooling cycles. That stability becomes increasingly valuable as processor packages grow larger and electrical connections become more densely packed. With a more stable foundation, engineers can position microscopic interconnects much closer together while maintaining long-term alignment. This significantly increases the number of communication pathways that can fit within the same physical area. More connections mean processors, memory, and specialized accelerators can exchange information more efficiently, reducing delays and allowing the entire package to function as a more unified computing system. For AI workloads, that improvement is particularly important. Training modern language models and running advanced inference tasks require enormous amounts of data to move constantly between different components inside the processor package. The faster and more efficiently that information travels, the less time the hardware spends waiting for data to arrive. In many cases, system performance depends not only on how powerful each individual chip is, but also on how effectively every chip communicates with the others. Glass also improves signal integrity. Electrical signals traveling across its surface experience less distortion and interference than they typically do through conventional substrate materials. As communication speeds continue rising, preserving signal quality becomes just as important as increasing processing power. Cleaner transmission allows chips to operate more reliably while supporting the ever-growing bandwidth demands of artificial intelligence. Heat management provides another important advantage. Although cooling ultimately depends on the complete system design, a stable glass foundation helps engineers create package architectures that distribute thermal stress more evenly. Better thermal behavior allows processors to sustain peak performance for longer periods instead of reducing speed to protect themselves from excessive temperatures. Taken together, these benefits represent far more than incremental improvements. Faster communication, greater connection density, improved reliability, cleaner electrical signaling, and enhanced thermal stability all contribute to one outcome: AI systems capable of handling larger workloads with greater efficiency. In previous generations of semiconductor development, shrinking transistors delivered the biggest performance gains. Today, many engineers believe future advances will come from improving the entire package surrounding those transistors. And if that proves true, glass substrates may become one of the most important enabling technologies of the AI era. It's easy to think of glass substrates as just another engineering improvement buried deep inside a semiconductor package. In reality, their impact could extend far beyond the companies that manufacture chips. If this technology delivers on its promise, the effects will ripple across nearly every industry that depends on high-performance computing. Artificial intelligence is the most immediate example. Training today's largest AI models requires thousands of processors working together for weeks or even months at a time. During those workloads, enormous volumes of information move continuously between processors and memory. Even modest improvements in communication efficiency can translate into meaningful reductions in training time, lower energy consumption, and better utilization of expensive computing infrastructure. For cloud providers and data center operators, those gains carry significant economic value. Building modern AI infrastructure demands billions of dollars in investment, with electricity and cooling representing a growing share of operating costs. If improved substrates enable processors to exchange data more efficiently while maintaining higher sustained performance, companies could process more AI workloads without proportionally increasing power consumption or expanding physical facilities. Small efficiency gains, when multiplied across tens of thousands of servers, become substantial financial advantages. The benefits extend beyond artificial intelligence alone. Scientific simulations, climate forecasting, pharmaceutical research, aerospace engineering, financial modeling, and advanced manufacturing all rely on increasingly powerful computing systems. As processor performance improves, researchers can analyze larger data sets, complete simulations more quickly, and accelerate discoveries that would otherwise require far more time and computational resources. There is also an important economic dimension to this transition. The companies that establish leadership in glass substrate manufacturing may occupy a strategically valuable position within the semiconductor supply chain for years to come. As demand for advanced packaging grows, suppliers capable of delivering reliable, high-volume production could become essential partners for processor manufacturers across multiple industries. In that sense, this story is about far more than a new material. It is about how a seemingly overlooked component has the potential to influence the economics of AI, strengthen global technology supply chains, and shape the pace of innovation across industries that increasingly depend on advanced computing. When people look back at major technological shifts, they often remember the headline innovations, the products that reached consumers, or the companies that became household names. What they rarely notice are the quieter breakthroughs that made those achievements possible in the first place. Glass substrates may become one of those overlooked turning points. For decades, the semiconductor industry advanced primarily by shrinking transistors. That strategy transformed computing and fueled everything from smartphones to cloud computing. But as physical limits become increasingly difficult to overcome, progress is beginning to depend on something broader than transistor size alone. The performance of tomorrow's processors will increasingly reflect how effectively every component inside the package works together. That is why advanced packaging has become such an important area of investment. Improvements beneath the processor can unlock faster communication, greater efficiency, and more reliable performance without fundamentally changing the processor architecture itself. In many ways, the next chapter of semiconductor innovation is being written not only on the chip, but underneath it. The competition is still unfolding. Companies across the United States, Asia, and Europe are investing in new manufacturing facilities, refining production techniques, expanding patent portfolios, and strengthening supply chains. No clear winner has emerged, which makes the next several years especially significant. The organizations that solve these manufacturing challenges first could shape the future of AI infrastructure for much of the coming decade. Perhaps the biggest lesson is that technological leadership rarely depends on a single breakthrough. More often, it comes from recognizing opportunities that others overlook. While much of the world continues to focus on processors themselves, another race is quietly taking place beneath them, one centered on materials, manufacturing, and precision engineering. And that raises an interesting question. As new technologies become increasingly essential to the global economy, is it healthier for innovation when multiple countries share leadership across the semiconductor supply chain? Or does concentrating expertise in a smaller number of regions ultimately accelerate progress? Let us know what you think in the comments below. If you enjoy thoughtful analysis of the technologies, industries, and supply chains shaping tomorrow's economy, subscribe to Future Structures. We'll continue exploring the innovations that often stay out of the headlines, but have the potential to redefine entire industries. If the advantages of glass substrates are so compelling, one obvious question follows. Why hasn't the semiconductor industry already made the transition? The answer is simple in principle, but incredibly difficult in practice. Producing semiconductor-grade glass is one of the most demanding manufacturing challenges in modern electronics. Success depends not only on the material itself, but on achieving an extraordinary level of precision throughout every stage of production. Unlike conventional glass, semiconductor substrates must be manufactured with almost perfect uniformity. Their surfaces have to remain exceptionally flat across large areas while maintaining microscopic tolerances that leave virtually no room for error. Even the slightest variation can affect how chips are assembled or how electrical signals move through the finished package. The complexity increases further when engineers create the tiny vertical pathways that carry signals through the glass. These microscopic openings, known as through-glass vias, must be drilled with remarkable accuracy. Each one has to be positioned exactly where intended, maintain consistent dimensions, and avoid creating tiny defects that could weaken the material over time. Glass is naturally rigid, which gives it excellent dimensional stability during operation. However, that same rigidity also makes manufacturing considerably more difficult. Introducing thousands, or even millions, of microscopic features without causing fractures, internal stress, or hidden imperfections requires specialized equipment and highly refined production techniques. The challenge extends well beyond engineering. Manufacturers must also achieve consistently high production yields. In semiconductor manufacturing, a process that works inside a laboratory has little commercial value unless it can be repeated reliably across thousands of production batches. Every defective substrate increases costs, slows production, and reduces profitability. Reaching that level of consistency often requires years of experimentation. Companies must refine materials, optimize processing methods, improve inspection systems, and gradually eliminate sources of failure before large-scale manufacturing becomes economically viable. It is an expensive process that demands patience as much as technological expertise. This is precisely why glass substrates have become such an important strategic opportunity. The competitive advantage no longer belongs solely to the company with the best research laboratory. It belongs to the organization capable of transforming promising technology into dependable, high-volume manufacturing. History has shown that in the semiconductor industry, mastering production often creates a stronger competitive position than inventing the technology itself. As a result, the race is no longer simply about discovering better materials. It is about building factories, developing specialized manufacturing processes, training skilled engineers, and achieving production quality that customers can trust. Those capabilities take years to establish, which means companies investing today are positioning themselves for a market that may define semiconductor packaging throughout the next decade. For years, discussions about semiconductor leadership revolved around one capability above all others: manufacturing the smallest and most advanced transistors. Countries invested billions of dollars in fabrication plants, export controls, and research programs because the prevailing belief was straightforward. The nation that controlled leading-edge chip production would ultimately control the future of computing. That strategy remains important, but it is no longer the entire story. As AI systems become more sophisticated, companies are discovering that performance gains can come from more than transistor scaling alone. Advanced packaging, the process of integrating processors, memory, and communication components into a highly efficient system, has become an equally important frontier. And at the heart of that transition lies the substrate. This shift carries strategic implications that extend well beyond engineering. Unlike cutting-edge chip fabrication, which depends on an extremely limited number of highly specialized manufacturing tools, improvements in advanced packaging rely on a different combination of capabilities: materials science, precision manufacturing, process engineering, automation, and production expertise all become central to the equation. That changes where competitive advantages can emerge and broadens the range of companies capable of contributing to the semiconductor ecosystem. For governments seeking to strengthen their domestic technology industries, this represents an important opportunity. Building world-class chip fabrication facilities requires enormous financial resources, years of construction, and access to highly specialized equipment. Developing expertise in advanced packaging presents a different pathway, one that still demands substantial investment but allows countries to compete in another critical segment of the semiconductor value chain. This realization has gradually reshaped industrial strategies around the world. Rather than focusing exclusively on transistor technology, policymakers are increasingly directing funding toward packaging research, advanced materials, and next-generation manufacturing techniques. Universities, research institutions, equipment suppliers, and private companies are collaborating more closely than ever to accelerate innovation across the entire semiconductor ecosystem. The growing interest in glass substrates reflects this broader change in priorities. What once appeared to be a niche materials project is now viewed as a strategic technology with long-term implications for AI infrastructure. Companies that establish expertise early could become indispensable suppliers to processor manufacturers, cloud computing providers, and data center operators for years to come. Perhaps most importantly, this emerging competition demonstrates that semiconductor leadership is becoming more diversified. Success will no longer depend solely on who builds the smallest transistors. It will also depend on who develops the strongest packaging technologies, the most reliable manufacturing processes, and the most resilient supply chains. In other words, the race for the future of computing is expanding. The industry's next major advantage may not come from replacing silicon itself, but from reinventing everything that surrounds it. And glass substrates are quickly becoming one of the clearest examples of that transformation. Long before glass substrates became a mainstream industry discussion, Intel had already begun researching their potential applications in advanced packaging. Years of experimentation have allowed the company to build a substantial portfolio of manufacturing expertise and intellectual property. Rather than treating glass as a distant concept, Intel has spent more than a decade exploring how it could support future generations of high-performance computing. Today, that experience offers strategic flexibility. Beyond developing the technology internally, Intel has increasingly explored partnerships that allow manufacturing expertise to spread throughout the broader semiconductor ecosystem. In doing so, the company positions itself not only as a chip designer, but also as an important contributor to the packaging technologies that future processors may depend upon. Samsung has also accelerated its efforts. As one of the world's largest semiconductor manufacturers, Samsung understands that advances in packaging can be just as important as advances in chip fabrication. The company has established dedicated research programs and pilot production lines focused on glass substrate development while expanding collaborations with suppliers specializing in advanced materials. These partnerships are particularly significant because producing semiconductor-grade glass requires an entire ecosystem of specialized chemicals, manufacturing equipment, inspection technologies, and precision processing techniques. No single company can build that ecosystem alone. Success depends on a network of suppliers working together to solve increasingly complex engineering challenges. TSMC, the world's leading contract chip manufacturer, has likewise intensified its attention on advanced packaging. The company's leadership in AI chip production has been built not only on transistor technology, but also on its ability to integrate increasingly sophisticated processor packages. As customer demand continues to grow, maintaining that leadership requires constant investment across every layer of semiconductor manufacturing, including the substrate itself. By expanding research into next-generation packaging materials, TSMC signals that glass substrates are no longer viewed as a speculative technology. They have become part of the industry's long-term strategic planning. Another important player operates further upstream in the supply chain. Companies specializing in advanced glass manufacturing are working to develop the raw materials required for semiconductor-grade substrates. Producing glass with the necessary purity, consistency, and mechanical properties is an achievement in its own right. Without reliable suppliers capable of manufacturing these specialized materials at scale, even the most advanced packaging technologies cannot move into mass production. Taken together, these developments reveal an industry preparing for a significant transition. Rather than waiting for one company to establish complete market dominance, semiconductor leaders are investing simultaneously across research, manufacturing, materials, and supply chains. That creates a competitive landscape where multiple regions are advancing at the same time, each seeking to secure a position before demand accelerates. The outcome remains uncertain. No company has yet established an overwhelming lead in commercial glass substrate production. But the investments being made today will likely determine who supplies the foundation for tomorrow's AI processors. In the semiconductor industry, those who master manufacturing early often shape the market for